So let's start out with some basic definitions, and these are things that are going to get kind of used a lot when we start talking about reactions. Now there's two really big definitions when it comes to reactions. The first is what's called the reaction coordinate, which is generally represented by the letter S. Now the reaction coordinate is a very special term that's used to describe how a reaction proceeds along in time. Basically it's our time component. But it's very special because it follows the life of reactant molecules through the transition states down to the product molecules. So as we move forward along the reaction coordinate, we're moving towards products. As we move backwards along the reaction coordinate, we're moving towards reactants. So an example of this, if we had the reaction of a bromine ion, Br-1, plus CH3Cl. This is a very common reaction given as an example of what are called SN1 reactions in organic chemistry. As this reaction proceeds along, it will go through an intermediate state. And in this intermediate state, we have chlorine and bromine switching places. And when we finish, we end up with bromine on the carbon and a Cl- in the product. So basically we have bromine substituting for chlorine. Now, to describe the progress of this reaction, we're going to draw a line across the bottom. This line across the bottom is what's called the reaction coordinate. This is going to be the letter S. Now, typically what's plotted against the reaction coordinate is the energy. So almost always it's energy versus reaction coordinate. And what we see is that when we start out the reactants and we move along the reaction coordinate, we're going to start from the reactants, go to the transition state, which is the peak energy as we move along the reaction, and then we're going to fall back down into the products. So the reaction coordinate starts down here, small values of S, we're starting with reactants. When we finish in time, we end it with our products. And somewhere along the reaction coordinate, we have our transition states. Now, a second idea, which we'll use quite a bit when we just talk about reactions, is what's called the extent of reaction. Now, the extent of reaction is represented with the letter X. Now, full disclosure, I'm left-handed, and when I was in college, I wrote left-handed, so I had nothing but uppercase letters to make my writing distinguishable. Well, come to find out, if you take chemical engineering at NC State, they love using the letter X. So they love using lowercase and uppercase X. And I just have this weird thing, well, I'll write the symbol for silver or lead using for the extent of reaction. This happens every now and then. I do apologize if you see it. It's just me being weird. If you ever see this symbol, it's the extent of reaction. Now, the extent of reaction has a couple of very unique properties that we're going to use. The first is that the extent of the reaction, if we multiply it by a reaction coefficient in a reaction, it'll actually tell us how many moles of that reactant we have. So if we had the reaction 2H2 gas plus O2 gas goes to 2H2O. And our extent of reaction is 0.500. If we want to know how many moles of H2 we reacted, we just simply take twice the coefficient on H2, and this would give us 1 mole of H2. So the reaction coefficient times the extent of reaction gives us moles of that particular product. If we want to know how much O2 we reacted, it's just simply going to be 1 times the extent of reaction. And this will tell us that we reacted away a half mole of O2. And again, extent of reaction times the reaction coefficient. If we want to know how much water we produced, it's 2 times extent of reaction. So we will produce 1 mole of H2O. So this tells us that in our reaction, if our extent of reaction is 0.500, we reacted 1 mole of H2, 2 moles of O2, and produced 1 mole of H2O. So this is one important property of the reaction coefficient. If we multiply our reaction coefficients by our extent of reaction, we're going to get moles of whatever we're interested in. Now, the second property we're going to exploit is that extent of reaction is also going to tell us the direction of a reaction. Now, some professors will tell you that extent of reactions always have to be positive. I did chemical engineering. We weren't taught that. What we're going to do is we're going to use extent of reaction to describe how far a reaction has proceeded when we work with an ice table. Now, if you're not familiar with ice tables, take a look at this video, go back through it with limiting reactions. Basically, what we're going to do, instead of having a limiting reagent, we're going to use an extended reaction. We're going to scale up our extended reaction to describe how many of our reactants or products are formed. When we put our value of X into the table and we solve our ice table, what we're going to work for is finding that value of X. Now, X can take on a lot of values depending on what your final expression ends up being. But the point is, you can get a lot of values for X. The only value of X that we can use, though, is the one that gives us a realistic answer. And that answer is one that has positive values for reactants and products. So this is the other property we're going to use in extended reactions. We can use X as a variable for solving how far a reaction proceeds for an equilibrium limit reaction, and use that also to solve for the concentrations of reactants and products after the reaction has reached equilibrium.